Good evening, everyone. My name is Sai Aditya, and we are here today for the technical webinar series at the cutting edge of composites, AI, and manufacturing that's co-sponsored by AIM for Composites, Ideas NRT, and SAMPI Baltimore Washington chapter. The topic for today's webinar is AGAPI, atomgpt.org API for Agentic AI in Material Discovery and Design. AIM EFRC is built to develop an AI-enabled inverse design approach for fundamentally understanding and integrating material manufacturing design of advanced polymer composites. Likewise, the IDEA's NSF NRT is a traineeship that focuses on training the next generation of STEM students to develop expertise across multiple disciplines, specializing in AI-enabled inverse design, advanced composites, and sustainable manufacturing. Our third co-sponsor, SAMPI Baltimore Washington, is a chapter of SAMPI, an international professional member society that provides information on new materials, processing technologies through chapter technical presentations, journal publications, symposia, and a host of other resources. Season 4, as mentioned before, focuses on researchers that are at the cutting edge of composites, AI, and manufacturing. And today's presenter is Dr. Kamal Chaudhary, an assistant professor in the Department of Material Science and Engineering with a joint appointment in electrical and computer engineering at Johns Hopkins University. His research focuses on atomistic materials design using classical mechanics, quantum mechanics, and machine learning methods to accelerate experimental discovery. Previously, he earned his material science and engineering from the University of Florida in 2015 and served as a staff scientist at National Institute of Standards and Technology, NIST. He is the creator of the widely used Jarvis or Joint Automated Repository for various integrated simulations, atomgpt.org, and ChatGPT Material Explorer infrastructures for materials design. He has published over 100 peer-reviewed articles and serves as an associate editor for Nature NPJ Computational Materials and is an editorial board member of Materials Today Communications, PRX Energy, and Machine Learning Science and Technology journals. He's a fellow of the American Physical Society and is an active member of TMS, APS, ACS, and MRS societies. We would like to acknowledge the AIM EFRC, which is an Energy Frontier Research Center by the US Department of Energy under the Office of Sciences, and the National Science Foundation Research Traineeship Inverse Design Training in Advanced and Sustainable Composites under Award 2244-342 from the NSF Division of Graduate Education. We would also like to thank the SAMPI Baltimore Washington chapter for being one of the co-sponsors for this event. Our webinars occur monthly and the information is available on our social media channels. Thank you. And with that, I'll hand it over to Dr. Kamal Chaudhary.
Thank you, Sai. Thank you, Srikant. Thank you all for being here. I would like to acknowledge all the team members here who made it possible about a month ago or a couple of months ago with all the coordinations. My name is Kamal Chaudhary. I'm an assistant professor at Johns Hopkins University with Material Science and Engineering Department, Electrical and Computer Engineering Department, and also Data Science and AI Institute. I also hold a position at NIST as a research associate, and I was a staff scientist there for the past 10 years. So this is the outline of my talk. This is might be a different approach of looking for material design. So I will briefly talk about what is agentic AI. Then I'll talk about something called ChatGPT Material Explorer and its successor of atomgpt.org. And then we'll also discuss how to benchmark this kind of agentic infrastructure and some hackathon approaches. So let me start with very brief overview of the agentic AI frameworks. And before we go agentic AI, I thought, why don't we discuss about what is intelligence in general, right? So if you look into definition of intelligence on Wikipedia or any other book, the definition itself is not very clear. Some call it the ability to adapt to new situation, compared to something like memorizing fact? Or how does it generalize or extrapolate compared to just pattern matching? How does it reason for a particular problem rather than just mimicking situation or just providing perfect information? So these are some of the key differences in intelligence. And if you are interested in the epistemology or intelligence study in general, these are some of the papers. And I think this is important to know about these things before we talk about concepts such as AGI, like artificial general intelligence and so on. I think before we go in all these kind of things, it's better to understand what intelligence is. And so I just put a slide over there. And with that, this is a typical landscape of AI. So, just in general, AI you can consider as an umbrella term, which the idea is to mimic human brain or neurological functions. Then a part of this AI is machine learning, which deals with data set less than 500 or close to 500 data points. Deep learning usually requires neural network architecture, perceptron, and requires massive amount of data. Generative AI, based on a prompt, generates new content or new image. Agentic AI, instead of just producing content, tries to take actions, and that's a key differentiation of agentic AI compared to other AI models. So if you want to learn about deep learning and other AI methods in material science, we wrote a paper about this about 5 years, 4 years ago, and called Recent Advances in Applications of Deep Learning Methods in Material Science. And you can see it was published in Nature NPG Computational Materials and cited about 1,000 times. So it's a quite celebrated article in the field. Now, why do we need to go to the agentic AI, and why not just using AI for materials? So first of all, some of the limitations are materials discovery is quite slow. Whether you want to discover new alloy or new superconductor, they are expensive and they are fragmented. Traditional AI can predict properties but cannot take actions. Scientific workflow require multi-step reasoning, not just one if-else statement, but it requires tool chaining so that it can connect multiple stages and steps and be iterative, not just a one-shot process. The question we ask, can we make or can AI behave like a junior scientist? If not replace the scientist, can we make a junior scientist for performing all tedious or repetitive tasks? But the problem we encounter when we try to have AI junior scientists is this hallucination, where LLM or AI models such as ChatGPT and so on can provide incorrect results with high confidence, or psychophantasy, where we are trying to have critique over a question, but it's trying to be optimistic, over optimistic about what you are doing instead of finding a fault or finding a or criticizing our approach. So it's sycophant nature. So these are the couple of key problems of using AI junior scientists technically, but also in other aspect is if you want to use something like a model, Claude or ChatGPT or Gemini, sometimes they ask for commercial API fees, and they're also black boxes. That means we do not have access to what is going underneath the model. Some of the outputs could be non-reproducible. So if you ask a question right now, 10 minutes from now, it will be a different response. So this is not good for science. Science wants reproducibility. And most of these data sets are trained on um, a huge data set from internet, like Wikipedia, New York Times papers, and so on. So it may not have specific knowledge of physics, chemistry, math, and biology. Although most of these AI frameworks are going in that direction anyway. So what can we do to solve this problem? There are a couple of approaches. Number one, we can teach them, that is, connect with scientific data sets and resources. So all these AI models, LLM models, we can connect it with a feature called RAG, tool calling, MCP, A2A, which we'll briefly discuss. And these are the frameworks which are also part of the agentic AI framework called, and this is I call teaching. Or you can train them where we take the model and fine tune at least some part of the parameter, not the entire model, on a custom data set using LoRa and parameter efficient fine tuning and so on. So we use both of these approaches to make AI models suitable for material science, because currently it's definitely not. So this is why we need agentic AI framework. Now, if you want to learn about agentic AI, these are the couple of PDFs that you can Google and probably find out as well, called A Practical Guide to Building Agents. This is from OpenAI. It's a 38 or 30 plus pages article, quite useful. Also, the Startup Technical Guide AI Agents by Google Cloud. This I personally used for building the AI agents like Atom GPT, so highly recommended. When you differentiate between predictive AI, you get output. So suppose you want to predict the band gap of a crystal. Okay. All right. So yeah, in predictive AI, you can predict properties such as models like CGCNN, Align, Magnet can predict property like formation energy, band gap, forces on atoms, energetics, powder excess diffraction classification, absorption energy, materials property prediction, one-shot invert design like variation autoencoder diffusion model. So these are all predictive models. Um, Generative AI, you can consider to produce contents. It can be text content, image content, audio content. It usually follows a pattern-based responses and waits for the prompts. Agentic AI does not need to wait for the prompt. It can take autonomous action. It can be goal-directed behavior. It can solve problems using tools and planning. It can call APIs, application program interfaces, search databases, and run calculation or perform experiments. So these are the key differentiation between agentic AI compared to generative AI and predictive AI. Let me start with a very simple example of strawberry. So if you go in atomgpt.org, which is a website from our group, and sign in with your Gmail account or GitHub or your own um, email and ask very simple question, how many are in strawberry? And you select three different models, GPT OSS from OpenAI, Llama model from Meta, and suppose we take Gemma model from Google. And hit search, hit click. Then you get these responses. For GPT OSS gives 3, Llama gives 2, and Gemma gives 3. So you can see even for this very simple test, sometimes the model hallucinate and hallucinates with high confidence. So how can we solve this issue? One of the way to solve this is connecting with API. So what is an API? You can think of an API which is a Python or other code hosted in cloud. So we can write a small code, this Python small code here, count R, which can take a string like S dot count R so that you can put strawberry, it will be exactly 3, reproducibly. So you can take this code, very 3 or 4 line of code, host using Fast API plus Amazon Web Service. And now when somebody asks in the chatbot, how many are in strawberry, the model, the LLM model, will talk to this API before giving its response. It will talk to the API, gets the data from there, and then give you a response. And this will always be 3. So this is how we um, make agentic AI work using LLM as a brain and API as hands. So what is the differentiation between static databases, APIs, and agentic AIs then? So static databases are quite common. So anytime nowadays you publish a paper in AI from materials, they'll ask you to put data either in GitHub or Figshare or Zenodo, Google Drive, or some open access repositories, which is great. But if you want to do something like a quick action, it's very slow. So because you have to download the data, you don't know the format of the data. Um, uh, Format the data, format the file. There's so many problems. So one of the way to make it accelerated is make the data as API, which is basically host it in some server, and then it becomes very fast. You can make a web app with it, and then people can connect their tool with it. So in general, if you are interested in AI for materials, whether you are theory or experimental person, consider having these 4 steps. You'll make a domain-specific data set. For instance, DFT database for superconductor, X-ray diffraction for some powders or whatever you are trying to do in your work. Make a data set. Make an API using Django, Fast API, or Streamlit. These are all frameworks for making API. Then some users they like instead of having API calling some sort of web app. So we will host data using API, and most of the current data structures or databases for materials use this approach. They have some sort of database, make an API, and have some sort of interactive web app with this. What we are talking about here is the next step, which is the agentic framework, which goes beyond just the database or web app and connects the API with the LLM as brain. Now, why agentic AI for material science is so hard? You saw that even for the case of strawberry, very simple example, some of the language model could struggle. If you think that material science is way harder than this, because uh, there are different types of data sets for different problems and tools. Like even if you talk about computational methods like density functional theory, molecular dynamics, there are so many approximations within it. Experiments have so many uncertainties. So making a database, a consistent database for everything in material science is very difficult. Also, materials are nearly infinite. If you look into the periodic table, 100 elements, and if you, even if take a combination of 10, it becomes 10 to the power 100 combination easily. And making a database of such a huge number of materials is just out of reach. Another problem is reproducibility. If you look into this Nature paper called 1500 Scientists Lift the Lid on Reproducibility, you'll see that only 0.5% to max 30% papers are reproducible. So more than 70% papers are non-reproducible, which is a challenge. So if it's not reproducible, your data is probably may not be super useful, right? Um, all the data that comes from an instrument or from theory may not have common schema or common format, and they need to be open API specification ready um, to make it an agentic framework. Some of the calculations are very slow, like DFT, MD, and it's for a real-time question answer. This may not be very viable, and also for experiments. And as I said, most of the agentic framework models like Claude, ChatGPT are proprietary. Although it's like few cents per call, it adds up and it's not really good for academic science. So we'll try to solve this problem. And we want to mention that based on these and many other features, material science is very hard. Look at this very simple example of Iron Man, where he's trying to generate an arc reactor using periodic table element combination, right? So he selects like cerium or other elements. So this is a very classic structure property performance relationship. And because there is no straightforward rule, we have to do this by trial and error. And that makes the material science problem, material design problem of alloy or whatever task you're doing super hard, right? So I just want to point out it's extremely difficult to make agentic AI framework for material science. Luckily, because of initiatives such as MGI, Material Genome Initiative, CHIPS, and now Genesis Mission, US government and many other governments are pushing in that direction to accelerate material design. And one of the framework that came from some of this work is called Jarvis, which is available at jarvis.nis.gov and now at atomgp.org with my Hopkins work and so on. And there we try to have DFT, force field, machine learning, and many other tools to automate or design or discover new materials. So this is quite different from many other data sets because it has end-to-end interoperable infrastructures, workflow, and APIs. One of the component of Jarvis is called Jarvis DFT. It has about 100,000 materials. We try to have high quality data compared to large volume data. So you'll have like van der Waals functional, improved band gap, spin orbit coupling. We converge key point for each of these materials, which actually pays off later. You'll see in superconductor design and other phonon calculation. We try to converge energy forces. So this makes the whole DFT or density functional theory calculation super slow and compared to 5 to 10 times slower than using a high throughput. But in the end, it pays off. We have properties like elastic tensor, piezoelectric tensor, dielectric tensor, electric field gradient, superconducting transition temperature, 2D monolayer data, Raman spectra, Seebeck and power thermoelectric coefficient, solar cell efficiency, scanning transmission electron microscopy, and scanning tunneling microscopy images, surface data, interface data, defect data, and we will try to make this all available through API and then connect to the LM using Agentic AI. And the database is used over 200,000 users, about 2 million downloads on Figshare, You can see these are probably the highest download on from any researcher around the world. 2.4 million download on Fixture. Same with the code, about 50 articles, 6,000 citations, and a lot of great insights on from the community. Now, the first component is done, almost ready, I would say, is the database part. We have the database. So how to make agentic framework for this? So in early 2024 or in the end of 2023, I personally saw this post called Custom GPT as a Google News on my phone. And here, the Sam Altman, who is the CEO of OpenAI, he discussed about how you can use ChatGPT for your custom version as a custom version. You can now create a custom version instruction extra knowledge. And I thought, why don't we do this for material science? And the idea is quite simple. If you go to chatgpt.com/gpts or explore GPTs, you can give your own name, like I call it a material explorer, give some description and instruction and some few more content, how it interacts with external data set. Now the ChatGPT can interact with outside data sets, high fidelity data set, before it gives response. So in this way, it can reduce hallucination, reduce psychophancy. And that was the idea behind custom GPT. So for example, if you ask a question, find all the materials of aluminum oxide, then it will talk to Jarvis or external tools and then give the response instead of uh, giving its own LLM-based response. We did not solve all the problems of material science in ChatGPT, Material Explorer. We had only three things: database search, graph neural network prediction, and archive search. That's it. And this is a demo how using agentic feature, the hallucination LLM can be reduced. We compared the GPT 4.0 back then with CamCrow and ChatGPT Material Explorer. We saw that for many of the cases, the GPTs are actually quite powerful, but for some domain-specific tasks, such as predicting properties or finding materials in a specific data set, these materials hallucinate crazy. Like they do not perform even close to reasonable job. And that's why we need agentic feature, especially for material science. It actually made a lot of noise or a lot of news in the community. So a lot of people made nice YouTube video about this. Johns Hopkins published several articles about this, and it becomes in a way quote unquote viral in the material science community. So this is not the only infrastructure. There are many other agentic infrastructures coming out. For example, this from Gabe Gomez Group, autonomous chemical research with large language model, ChemCrow from Andy Wright, Philip Solar Group, Elegante from Alana Spuruguzzi Group, um, this paper from Marcus Buehler from MIT, LAMP, SciTool agent, ChatGPT Internet Explorer, and of course, AGAPI agents, which is our current work. Of course, there are many others coming out, but these are some of the examples of how agentic AI is changing material design. Now let me take you to the next level, which is the atomgpt.org. The website looks like this. You can go to atomgp.org. You can sign in with your Google or GitHub or just using email, totally free of cost, no charges. The special feature about this infrastructure is it hosts open source models. So now uh, it's not a black box anymore. At least we know what model we are using compared to something like ChatGPT. Uh, Material Explorer, we are using ChatGPT proprietary model. It can perform several domain tasks like searching materials, property prediction, machine learning, force field, protein structure analysis, X-ray diffraction, literature search, web search. Your chat data is never stored, which is very important. So one of the problem with the current models like ChatGPT is they can actually sell your context or data, which is pretty bad for scientific researchers. So we try to make sure we delete user data uh, after a month or so, and you can always export your chat data, but it's not our intent to train or use any of your data, which is quite important from academic perspective. We also provide features like technical features like function calling, tool calling, model context protocol, which are important for building agents. And AGAPI is published in the archive. This is the archive article. And currently, just in few months, we have 3,000 users. This is the Atom GPT Lab, AGAPI, Atom GPT API um, code is available online. And also, if you are new in the field of AI for materials, think how you can make your data accessible as API. And hopefully, we can work together to connect in Atom GPT API. Either you are a theory expert or experimentalist, it does not matter. So let's see how does this AGAPI things work, AGAPI infrastructure work. So as I said, AI agent can be considered as a combination of three things: brain, the LLM or generative AI model, API, which are the hands, and orchestration. So suppose you ask this question: study the effect of nitrogen substitution in silicon carbide semiconductor. Find the 3C silicon carbide structure in Jarvis DFT, reports its properties, substitute a carbon atom with nitrogen, optimize the structure, predict X-ray diffraction pattern, then show the STEM image, predict the properties in Align, in SlackConnect, do some literature search, and then make a report. Now, this used to be the case of a undergrad student working on a particular topic. Now you can do this kind of complicated task in a chatbot because of agentic AI. And there are two components: your brain or LLM model like GPT, OSS, Llama, or any other open source model. Tools such as Jarvis DFT, Align, Diffract GPT, SlackOnet, these are all custom based model. And then infrastructure called OpenAI agents or MCP, LangChain, etc., to plan, execute, or summarize these connections, which can take autonomous actions. These are kind of infrastructure of AGAPI, how it is designed. You can find not just LLM, but also several APIs which are available um, in the Atom GPT, and you can connect in your own tool if you like, free of charge. We do have some rate limits just to avoid any sort of um, over functioning of the resource, but other than that, it's totally publicly available and open source. And another thing is we also uh, provide API as web apps. So you can see, for example, if you go to Atom GPT, click on apps, you can have this as individual web app as well. And it's also getting integrated now in the chatbot itself so that you don't have to go to individual web app and stuff. You can just chat about it. That's the idea of agentic AI. Now let me start with a very simple example. First, you install AGAPI as people install AGAPI. Go to atomgpt.org, get your API key, profile, setting, account, API keys, and now you can interact the AtomGPT directly on your notebook or your computer instead of going to the website. So you can ask very simple example, for instance, what is the capital of US? So now because it has the API key, it will connect to it and give the response. Most importantly, it can talk to interact with the material science specific database. Suppose you're looking for find me all aluminum oxide material and use tools. Basically, it means use data sets or resources which are authentic. Then it will go talk to them, make the summary, and then present the result in this nice table and also explain what these things mean instead of just putting the number, which is quite important, especially for newcomers in the field. If you put the use tools as false, then it will just give the data as that from the LLM itself. So which is can be hallucinated, can be incorrect. You can ask in many ways, not just if else statement wise kind of approach, but also you can ask in natural language, like how many materials are superconductors, which is some of the work we did for our finding superconductor materials about 3 or 4 years ago. This was one of the first full atomic structure database for superconductors. So now you can interact using natural language instead of coding or any search like this. You can compare properties of materials. Again, what's under the hood it is doing is getting data of each individual material and trying to explain it to you what it means instead of just giving the output. If you, probably some of you are familiar with graph neural network, especially is quite relevant for atomistic simulation and accelerated atomistic simulation. So about 5 or 6 years ago, we have proposed this framework for atomistic line graph neural network, which has been cited about 600 times. So it was used to predict the properties of atomic structures way faster than something like density functional theory. And now it's integrated in a natural language, so you can ask for a particular ID or a particular material, can you predict the properties using Align? all because of the agentic feature. And as I said, it's also available as a web app. So if you're not familiar with, if you're not liking the natural language, you can just put your atomic structure and hit predict properties, and it'll give you the predicted property in a few seconds compared to running DFT calculation or running experiment and so on. This can be used for machine learning force field optimization. This is a recently quite hot topic for computational material science. So we built one of the first universal or unified machine learning force field called AlignFF, and it's now integrated in an agentic way inside Atom GPT. So you can have atomic structure. It can ask to optimize the crystal structure, and it can predict the optimized structure for you. Not just one or two stages, you can see up to 10 stages. So find the materials, make a supercell, substitute atom, do X-ray diffraction pattern analysis, calculate band structure. Band structure in a chatbot. This was facilitated from this framework called Slackonet, which we developed about a few years, just last year, I think, which is a universal model for predicting the electronic band structure. The graph neural model usually cannot predict the electronic band structure because it uses something like bonds, angle, distances, and not really electronic structure data, which makes it challenging to predict band structure. So now you can, in the chatbot or in an agentic way, you can design materials using natural language, just using under the hood using these fast AI models. Of course, if you don't like the natural language, you can also go to the web app and predict band structure in few seconds compared to something like DFT. You can, most importantly, for at least for semiconductor design, interfaces are quite important. So, for example, if you want to make an aluminum nitride, gallium nitride interface, you can just chat about it in an agentic way. It will generate atomic structure for you, which is quite interesting compared to, download this software, that software. There's so many version compatibility issues, read documentation. Instead of all of that, you can just hopefully just put the prompt and it will generate the structure for you. These were all related to theory. How about experimental analysis? So suppose you want to predict the X-ray diffraction of a particular material, like gallium nitride. You can chat about it and it will predict the X-ray diffraction pattern, like 2 theta intensity, as a forward model. Or it can be used for inverse model, like if I have a diffraction pattern, can you tell me what structure it is? So this is a framework we have developed called Diffract GPT. It's quite popular nowadays. You can see it has been downloaded about 240,000 times, which is in a way more than DeepSeek as well. So it's in a way approaching that of a natural language model, the mainstream natural language model. And the idea is you represent a diffraction pattern like this as a natural language. So if a chemist look at this diffraction pattern, it will say here's a diffraction pattern. There's a peak at 20 degree, 30 degree, 90 degree, and so on. And these are the peak intensity values. And just as a text is your input, and your output would be the CIF file or the postcard file or the atomic structure file. And you can do mapping of text to text. Now you can have scenarios where you have no chemistry data, element list data, or chemical formula data. So we can, for instance, take the chemical formula and the diffraction pattern described in a natural language, and it will generate the crystal structure for you. So these also available in the agentic framework. Here's an app example. So if I go to atomgp.org/xrd, you can put your chemical formula, X-ray diffraction pattern, wavelength, and we'll try to find the best match material. Or if it does not exist in a database, we'll make it for you. So Lab 6 is a standard reference material. So it was able to generate the X-ray diffraction pattern. But what if the material does not exist in any database? So suppose there's a new material, then we can suppose we put, instead of lab 6, I put a nitrogen there and hit the analysis again. Now you'll see that it was not able to find any materials with this chemical formula. So of course it won't be able to match. But Diffract GPT will be able to generate atomic structure for you, which is power of the GPT model. So you can think of Diffract GPT as the AlphaFold for material science and engineering, where it's trying to generate atomic structure from the diffraction pattern or a chemical formula using GPT models. It can be used for literature search. Suppose you are looking for bismuth telluride, you can find papers about bismuth telluride, also materials about bismuth telluride easily. So it's quite easy to to do some literature search instead of going to Google Scholar or something like this. And it can also, we have seen that some of the conferences such as NeurIPS is seeing a lot of papers with hallucinated or wrong references. Now we can use something like this to make more appropriate references. Finally, how do we benchmark this? So it's very difficult to benchmark agentic AI models for unknown materials. So let's start with well-known materials. So what we did, we asked the uh, GPT OSS LLM model and GPT OSS plus the API model to predict the band gaps, bulk modulus, superconducting transistor temperature, solar cell SLME coefficient, and dielectric constant of few well-known materials. Okay. What we found was quite interesting and not expected actually. We found that the tool augmentation, which is basically the agentic AI, is not universally beneficial. Its effectiveness depends on three factors. Number one, database quality, standardization of computational protocol, and whether the material is well documented. So suppose we are talking about magnesium boride, which has superconducting transition temperature of 39 Kelvin in literature. The GPT OSS model will give you a response very close to the known data, of course, because it was trained on that books or literature article. But from perspective of DFT, it gives you 33 Kelvin because it has several approximations in it. So it will give you lower TC, lower transition temperature, and so on. So this is an example how the we should probably provide both the responses, one from with tooling, one without tooling, and do some sort of analysis with it, right? Instead of just having one number. And this is quite important, especially when this is a new material. Then we have no idea whether the data in the literature exists at all, like bismuth telluride, manganese bismuth, or manganese titanium or something. It may not exist. And there we do have to rely on the agentic framework compared to only LLM response, which is quite important. We recently organized a hackathon called Agentic AI for Science hackathon at Hopkins, and we had about 120 participants, and we are actually working on a paper. Maybe some of you participate on this, so you'll be part of that paper as well. We'll be having another one soon next year, so stay tuned. These are some of the collaborators we have. If you have any idea, feel free to reach out. And some of my grad students and undergrad students, we thank them for their continuing work. This is my group page. So in summary, I want to point out that future is agentic. So there is no way you can avoid it. Even in current framework like ChatGPT, Claude, under the hood, they are using agentic features. So suppose you ask, find me papers about this, they will go and search in a web browser or some other data sets and then give a response to you. So this is the future. Now, it's very important as a researcher to share your data as an API instead of just putting a paper out there or putting some data in Figshare or something. If you want visibility, if you want people to actually use your data, it's very important to learn about how these things work. And nowadays, it has become super easy compared to when I started in this field, thanks to all these Gen AI models. So these are some of the contacts I have. This is my email address if you have any question. This is the GitHub page of AGAPI. This is the website atmgp.org where you can make an account. This is the archive link for the AGAPI agents. Also, you can connect me on social media, LinkedIn. I have a lot of YouTube videos on my YouTube channel about material science, data-driven material science, and these are some of the papers. So with that, I would like to thank you again for your time, attention, and Sai for inviting me, and happy to answer any question if I have. Thank you.